Hey, AP Chem, it's Mrs. Audiemeyer back with some more fun stuff having to do with bonding. Hopefully you guys are getting good at drawing your Lewis structures. You've dusted off the cobwebs and you got all your questions cleared up for drawing different Lewis structures for compounds, because what we are going to talk about now is something called internuclear distance. And if you think about the word internuclear, inter means in between. Nuclear means the nuclei. So internuclear distance just literally means the distance between the two nuclei and bond length. So what we're going to be paying attention to is when you draw that Lewis structure, how long is the actual physical distance between maybe that H and that C that you drew, or the O and the other O in the compound. And there are a couple of things that hopefully kind of are familiar to you that affect the distance between the two nuclei, or the bond length is what we call it, and the energy that a bond has, or how strongly two things are bonded together. And so that's what we're going to be kind of talking about in this first part here. So if you think about a chemical bond, we talked about a covalent bond. A covalent bond is an overlapping of two electron shells, okay? So we've got two atoms that come together and one shell overlaps with another shell and their valence electrons intermingle each other. Now there are a couple of different forces that go along with that intermingling. There is an attractive force that shows up between the protons in one atom and the electrons in the other. And we know magnets, opposite charges attract. So if I have a positive proton, that is going to be attracted to a negative electron. And it's kind of similar in our actual atom size that we have the attractive forces with a proton and an electron as well. But when we make a bond, the protons in one atom are attracted to the electrons in the other, and vice versa. So green means great, good, go. We're attracted. There is also a repulsive force that happens between the two protons of those two atoms, the two areas of protons. So if I bring protons together very close to each other, because they are both positive, they are going to repel and push away from each other. So anytime that we have a chemical bond that forms, there are those two interactions at play. And just like with the size of an atom, where we settle on a balance of positive attractions and those repulsions that happen, the length that two atoms settle next to each other, or the distance between the nuclei of those two atoms that settle next to each other, are again a balance between attractive forces between oppositely charged things and repulsive forces between things that are the same charge. And so what ends up happening is that one thing that they like to ask you questions about is taking a look at a graph of how far away two atoms are from each other and what that looks like in terms of their energy. So what you have to keep in mind is that when two things are oppositely charged and attracted to each other, that is a beneficial thing. And if I can get two things to kind of stick together, that generally drops their energy. And if I have two things that are very much repelled by each other, that is going to increase their energy. And so what you will see is you will see kind of a graph that looks like this. Now, this is a potential energy diagram. So what you have to think of as zero is kind of like your baseline. If your potential energy goes down, what that means is whatever you are doing to that thing is stabilizing it. So if I have a negative energy, kind of like we talked about ionization energy and electron affinity, if you see a negative energy value, that means that that's good for those atoms. So when I see this graph here, anything that's kind of hanging out below the zero line is good. Anything that's positive means that those two atoms now have higher energy than they did when they were kind of separated, and we don't want that. All things in nature try to keep things as low energy as possible because it's work to keep things in high energy. So what happens is you can think about this x-axis as internuclear distance, like it says, but I also think about it as the movement between two atoms. And I actually read this kind of different. I know that most people think of it as a left to right reading graph, but in this case, I actually think about these graphs as reading right to left. So what you kind of want to think about, and I have two tennis balls here, okay? So what you want to think about is the right-hand side of the graph here where it says no overlap or attraction. It starts off with two tennis balls, or in this case, two atoms that are so far apart that they do not even have any attraction, period, to each other. So the attraction of the protons in one atom to the electrons of another, not there. And then if we keep moving from right to left on our graph, what it's doing is it's showing the energy benefit when these two things move together. So once these two atoms get close enough together, there starts to be that attractive force. And so the attractive force between the electrons and the protons, that starts to make these drop in energy. And so that's what you are seeing in the graph on the right-hand side here. So if they're far enough away, they are not going to be attracted to each other. But what happens is as you get the two nuclei closer to each other, you start to see this dip in energy. And that's because the attraction between the oppositely charged particles in the other atoms start to cause a benefit or an energy reduction for your atoms. So as I get closer and closer and closer, that benefit grows and grows and grows because my positive and negative charges can get closer to each other. And the closer they can get, if you kind of think about Coulomb's law, the closer they get, the stronger that attraction is. So what happens is they get closer and closer. And at some point, and I can't do this with tennis balls, there is a minor overlap. We'll kind of imagine you can sort of see that there. Okay. There is a minor overlap. And what ends up happening is there is a magical point where we hit the best benefit for the oppositely charged particles being close to each other while minimizing the repulsions. Because what ends up happening is if I take these atoms, and I can't do this, but let's say I squish them closer and closer and closer. Oh, struggles here, okay? Eventually what's going to happen is if I get my two nuclei so close together, the two positively charged areas in those nuclei are going to push away from each other and overcome any benefit that you would potentially have for bringing those positive and negative charges together. So it's kind of like, if you think about this graph, the graph is nothing, not attracted, not attracted. Ooh, little attraction, that's good. And then when we hit this bottom part here, or this minimum part of the graph, that is the sweet spot between the best attraction minus the repulsion that we talk about. And that low point in the potential energy is where the two atoms tend to sit on average next to each other. Now, a bond is not like a static thing, so it moves. A bond between two elements can vibrate and rotate and that kind of stuff. But in general, when we talk about a bond length, it's the average distance that these two atoms settle from one another, okay? And then if I keep pushing it too far, you've gone too much. So here is an example of some actual data for hydrogen atoms. So we have potential energy here, and then we have internuclear distance. So if we start, again, I read these from right to left. When we start at the right distance, if we are a distance of 300 picometers, which is really tiny, away from each other, they are not close enough to each other to have an attraction between the protons in one and the electrons in the other, and it doesn't do much. If I cut the distance between those two nuclei in half to a distance of 150 picometers, in that case, my potential energy has dropped, and that drops because the protons in this guy are attracted to the electron in this guy, and vice versa. So there's starting to be that benefit of them getting closer together. And then what happens is they get closer and closer and closer, and when they hit a distance of 74 picometers between each other, that is the best combination of attractions of the opposite charged particles, not dealing with too much repulsion from my nuclei. And then what happens is if I try to squish them any closer together, in this case 45 picometers distance from there, what ends up happening is I have this huge increase in energy. And that's because those two atoms now are very uncomfortable, because essentially you're holding two atoms together that want to push away. And so that's why you see this huge spike in energy that's happening. So we're getting closer as we get to 150. The sweet spot is that minimizing repulsions while maximizing attractions. And then once you go past that point, you start to get too close. And up here, we have too many repulsions and not enough attractions to balance that out. Okay. Here is a chart of some bond length and bond energies that go with that. So if I go back for 1 second, down here, this negative 432, that is the potential energy gain that happens by hitting that sweet spot. So when I get my two nuclei in that perfect distance from each other, they drop 432 kilojoules worth of energy for every mole of those bonds, which is significant. Okay, that is called the bond energy. So here is a chart of some bond energies, and I have this area here circled because I want to kind of round you guys back to Coulomb's law. With Coulomb's law, we talked about two things happening. We talked about charges causing problems and distance between two nuclei causing differences in the strength of a bond. Now, it's not quite the same because we don't have charged particles, but the distance between the two does make a difference. So if you think about fluorine, chlorine, bromine, and iodine, those guys are all in the same family. They're in the halogens. And as you know, as we go down a family, the size of the nuclei, or not the size of the nuclei, the size of the atoms get larger. And so if you look, the fluorine to fluorine bond has a bond length of 142 picometers, and its, excuse me, its bond energy is going to be 158. If I look at Cl, now Cl is a bigger bond and it's stronger. There are some weird things that happen here, and I should have probably looked at this a little bit more closely. Fluorine always causes problems because it's fluorine. Okay, maybe that's not the best example, but let's look at chlorine to bromine. Now, bromine is bigger and it has a lower bond energy, and then the same with iodine. Iodine is larger and has an additional lower bond energy. So you can't look at this as a perfect trend, and you will find out as we go along with some of these things. Fluorine is a problem child. Nitrogen seems to be a problem child too, but we see general patterns where the closer things can get, generally the stronger the bond attraction is between them, and the smaller the size. Again, it's not consistent all the way, but it does happen. This chart is, by the way, in your workbook if you need to take a look at it. Okay, the next thing we need to actually talk about is multiple bonds. So you can think about like I said, bonds are not static. So if I have these two tennis balls, and these are two atoms, the bonds are not static. The distance between these two nuclei here can flex a little bit. If you think about the two atoms attached to each other with a rubber band, if I have one rubber band attached to two atoms, I get a pretty decent amount of stretch that happens between those two atoms. But if I have three rubber bands, like I would in, let's say, a triple bond, my amount of flex and stretch is not as good. And what ends up happening is the more pairs of electrons that are shared between two of the atoms in a bond, the tighter your atoms get pulled together. Because if you think about electrons kind of being evenly distributed around your atom, if I need to share more pairs of electrons, I got to get in closer to make that happen. Okay. And in general, what you see, and I have this kind of little table here for you, when we talk about multiple bonds, and this is carbon to a double bonded carbon to a triple bonded carbon. In the case of carbon, a carbon to carbon single bond is 154 picometers, and its energy is 348 kilojoules per mole. If I have a double bond, the double bond shrinks the gap between those two carbons, and then you end up getting a shorter bond and a higher energy. Okay, and this goes back to our Coulomb's law, and this pattern does actually work. Okay, and then the C to C triple bond tightens that distance up even closer, and then it makes it a higher energy. And so if you think about it, the more pairs of electrons we have, the tighter those things are, the stronger they hold together, so they have a stronger bond. If you notice, it does not double for the energy when you have a double bond. It does not triple when you have a triple bond. So there isn't a perfectly double gain when you have a double bond or a triple gain for its energy, but you do have a higher energy. So in general, a triply bonded carbon to carbon is going to be harder to break, or you get more energy when they form because those 3 pairs of electrons are attracted to each other, and vice versa. And again, as a consequence, they tighten up. So where I'm going with this is that once in a while, they will ask you a question where they'll give you a graph kind of like this, and they will ask you which thing matches up with the type of bond. So if I'd have C single bonds, C double bonded, and C triple bonded, and I'd be asked to match up with these things, what you have to think of is the depth and how low the energy drops, as well as how tight the bond is or how short the bond is. So if I look at these 3 curves or 3 lines on the graph here, if I look at C, C has the lowest energy change. And I should say maybe not lowest, but has the smallest energy change. So what this is telling me on this graph here, this blue line, is it's telling me that when I form this bond does not cause a huge drop in energy, which means it's not a super strong bond. Also, because distance is on the x-axis here, it tells me that this is the longest bond. Because where this minimal point here happens, this low point, it is the furthest away, or it's the longest distance. If I compare B, B has a bigger drop in energy, so that means it's stronger. And if you look, the point is closer to our y-axis here, which means that it's going to have a shorter distance. And then A, as A drops down, has a big drop in energy when we get to the sweet spot for our 2 elements. So that tells me that my bond here is very strong. When I get these 2 atoms together, they have a big energy decrease, and that's a really good thing for those atoms, but it tells me I have a very strong bond compared to C and B. And because it's short, because the distance isn't as big, it tells me it's a shorter bond. So when I look at these and I compare them, C, I know, is going to be the single bonded pair. B will be the double bonded pair, and A is going to be the triple bonded pair. And it has to do with this data here. So if I look at the carbon to carbon triple bond, it has the shortest length, so that's the shortest length here, and it has the biggest energy change, which is this big dip here, okay? C to C double bond is a little bit longer, so it stretches further out from the y-axis, and it doesn't drop as far because its bond energy isn't as high, and then C is the least. So when you see things compared like this and you see 2 kind of graphs together, or on your homework you're going to be asked to draw them, think about the peak, the low point is the most important. So if it's a stronger bond, it has to be lower. And if it's a shorter bond, it has to be closer to your y-axis, okay? This is kind of tricky. What we're going to be leading into is talking about something called resonance structures. And resonance structures deal with how long the bonds are between atoms. And there's some interesting data we're going to take a look at tomorrow. So try to give the problems that I assign you a try, and we will chit chat about resonance structures tomorrow. All right, good luck.